Hi, I'm Rion Gipson-Hansen.
Hi, I'm Matt Kinney.
I'm Brady Robinson.
And I'm Nathan Giefer, and this is our feedback final project.
For our project, we decided to model a self-driving car, specifically the braking system. This system can be represented with a mass and a damper, with the inputs being the force of the brakes and the output being the position of the car. This system can be modeled with a transfer function, with the output being velocity and the input being the force, and the transfer function being equivalent to 1 over ms plus b.
This is our preliminary analysis of our transfer function. To achieve the step response of our transfer function, we gave the variables for mass and damper were 1,000 kilograms and 100 newton seconds per meter respectively.
So with this preliminary analysis, the rise time and settling time are super big. So the settling time here comes all the way out to roughly 50 seconds, and that's way too big for our system. The rise time is also not quite appropriate, and rise time isn't as important in our system as settling time is. And then doing a root locus on the original transfer function, it results in this. There's just one single pole at negative 0.1, and this means that our system is always open loop stable. And based off of our assumptions, there's no need for any disturbance input into this, so we can ignore that. And then down here we have what our transfer function would be in the time domain.
So now to go over our design and controller specifications. For this design, we want to make sure our settling time is a lot lower than our initial calculations. On average, we want a settling time of roughly 3 seconds or less. We also want our percent overshoot to be about 0, considering that we can't have an overshoot in a negative direction. We won't be able to have a negative velocity. Along with that, we also want a steady state error of roughly 0. So then for our design and controller specifications, for this design we want to make sure we have a relatively low settling time, a lot lower than what our initial design had for us. For this, we probably want a settling time of roughly 3 seconds or less. Along with that, we want a percent overshoot of 0%, given that we can't overshoot in a negative direction since we won't be able to have a negative velocity. And we also want to make sure our steady state error is roughly 0. And for this, we went ahead and went with a proportional controller system where we have a unit step coming into our proportional control, into our transfer function, and then that loops back to our initial. So then solving for the proportional controller design, we found that our controller constant would be 1433.3. This value gives us a settling time of 3 seconds, and it also gives us a steady state error of 0.0648. And you can see the plot of the step response of our system, velocity versus time. And we can see in this new updated plot, our settling time is a lot closer. You can see it's 3 seconds there instead of closer to like 50. And finally, this will be the overall transfer function for velocity with respect to force using the proportional controller design.
We also analyzed a proportional integral controller, and for this is what the integral controller would look like. So there would be 2 values for it, and when you solve all that out with the velocity in respect to the input force, this is the transfer function you get. By making a controller such as this one, you eliminate your steady state error because of the S in the denominator, and this will make your steady state error completely 0, which is what we want for this situation. So once we solved for the constants of the Ki and Kp, you get a value of Kp equals 2,966. This is what controls the settling time. And then the Ki value was found with the Ki primarily being used to control the overshoot. So the only issue with a PI controller is it causes a large amount of overshoot. And this is seen in this function here where it will drop below 0, which in our application you cannot have a negative velocity. Once you hit 0, you have to stop. So even when you try to minimize the overshoot using a zeta value of 0.9999, which you want zeta as close to 1 as possible for this, which gives a percent overshoot of less than 10 to the negative 30, which is extremely small. When it shows up in the step response, it is a lot larger than what you want. But if you were to solve it this way, the KI would be 2,354. But because of this and the overshoot, we decided to go with a P controller as the best option.
As you'll see in the next couple of slides, the phase margin is infinity, as is the gain margin. Additionally, the gain on the system can be up to infinity. With all those components, the system will never, ever, ever become unstable. As you can see, the magnitude of our system starts from below 0 and goes down and never crosses the 0 axis. Additionally, the phase diagram starts from below 0 and peters out at around 90. The phase diagram will never cross negative 180. What this means is that there's infinite phase margin and gain margin for this system. Additionally, the time delay, because the phase margin is infinity, the time delay is also up to infinity. Given the information from the last slide, plotted here to the Nyquist diagram, you can see that no matter how much the magnitude is amplified and no matter how much the phase is shifted, the diagram will never encircle negative 1. What this means is that there's no unstable poles.
So in conclusion, this project, we identified our issue of an automated car coming to a complete stop. We couldn't have a large steady state error because then there would be the possibility of the car running into a pedestrian or something else. We had to create a decent rise time and settling time, more importantly settling time, because you didn't want the car to take 10 minutes to stop, and you wanted to eliminate the overshoot. So with all of that, we determined the best controller would be the proportional controller, based on the fact that you can control the settling time and minimize the steady state error associated with that. And doing a very slow stop, so starting at 10 kilometers per hour and coming to a complete stop, we determined the appropriate time would be roughly 3 seconds for the settling time. And this also presented a very minimal steady state error. And so once the force to stop has been applied to the system, it is run through the proportional controller and the transfer function before being fed back into the controller. And this will then eventually take the system back down to 0. So the controller we use is designed to give a minimum steady state error while also producing the desired settling time of 3 seconds. An analysis of the model shows that it is always BIBO stable, no matter the input force, change in gain, or change in gain or phase margin. So this ensures that the function will function properly every single time, no matter what is inputted or whatever else changes.